minute for the thing to kick in so I can stop it. All right. Oh man, we're up 20% from last time. We got 5 in here. Woo! Living on the edge. All right. So last time, I'm going to go ahead and get started, and apologies if I'm not quite at the right time. Oh, let's get these other couple people in here. Sorry. I guess I might as well wait to hit pause on this. Give me a sec. Oh my gosh. All right. So I want to spend about 30 or 40 minutes doing more forces on point charges because we didn't do many examples of that last time. And then I want to move on and do forces on wires and finish out the day with wires. Tomorrow in lab, we're building motors from scratch, and they're going to be really cheesy, but they're going to work. And so no pre-lab for that. It's come to class. We're going to be doing groups of 2 tomorrow in lab. So basically 2 people work together and build a motor. And if you make it work, good. We'll talk about lab more. And actually in class today, we'll explain some of the physics behind why motors twist. So I'm going to start on page 140 with question 28.4. 28.4. People in here. Okay. 28.4. And just as a reminder, before we get into this, well, screw it. Let's just do the problem. All right. It looks like we have a positive ion with charge plus Q and mass M. And so we got this plus charge here. And we're told it's moving this way, I think, with some speed V. Looks like there's some plates, right? Oh, that's not working too well, is it? Let's see if that gets better in an hour. Let's try this one. Oh, so nice. So there's some plates here. And obviously we can't see the whole plate. This is like going into the board, right? So this is the cross section of the plate. So there's a big piece of metal here and a big piece of metal here and a proton or some charge flying through there. Well, we were told both Q and M, those are both knowns too, right? Yep. And the distance between the plates is D. All right, all right. So we know that this distance here is D. All right. Between the plates, an external magnetic field is present with magnitude B directed out of the page. So there's a magnetic here, magnetic field, and that's an external field. Now, just to be clear here, you might be saying, what do I mean by this? Right? Oh, did I lose? No, I don't have a full setup here, but it looks a little bit like this. Right, here's a metal plate. So right, there's a plate here, there's a plate there, there's a hair on it. And then the idea is in between these plates, you can imagine there's this giant bar magnet here. I'm getting my delts worked out or whatever today. So the idea is there's a magnetic field between here and this proton's flying right between there. And it's right between 2 plates. Everybody got it? Kind of visual? Now in this case, so what do I mean by external? I mean just some big ass magnet. Some, not some, I don't know. More on that later. Okay. Just some big magnet. The charge travels horizontally and experiences no deflection. We're told gravitational forces are negligible. Right? So imagine this is like a tiny little ion. Okay, like in some chemistry experiment. It's going to fly right through here, and the gravitational force on an ion is going to be really low, right? Especially compared to any magnetic or electrical forces. Huh. What direction is the magnetic force on this ion? Does anybody remember the equation for magnetic force?
The force equals QV cross V0.
Okay, QV cross V, right? And remember, Q and V together are a little bit like current. Do you agree? There's charge moving, so that's a little bit like current times length, but whatever. What did I forget in this when I wrote this down? This should be a vector, agreed? If the inputs are vectors, the inputs of the cross product, okay, good. All right. Does anybody remember how we figure out the direction?
Right.
Right-hand rule. So you guys try it out. And remember, as a trick, I don't remember if I said this last time, on exam day, here's a cool trick, right? There's no rules. What I like to do is I like to move the paper. That way I'm not trying to do this crap and break my arm. So you can rotate the paper, because this is on your book right in front of you, and you can try out different directions there, but don't be afraid to move the paper around. Okay? What direction do you get? I heard negative J hat. Let's see. Line up the right hand, my fingers with B, curl them to B, thumb points down. All right, that's cool. That's the magnetic force. Agreed? Now notice in this picture, what I've done is this is speed, that's the direction. This is magnitude, that's the direction. This is the magnitude of the force, that's the direction. All right. Huh. Now, if this magnetic force was the only force, wouldn't this thing go downwards? We saw that beam. Okay. We want to cause an electric force to balance this out. What direction does the electric force need to be? Up. Is everybody cool that we need to balance this? If we want to balance this, we need an electric force up. Well, which plate needs to be at positive potential? Because remember, in order to create this electric field, what we've got is a set of parallel plates here, right? So when we're doing that, which plate needs to be positive? The bottom one, right? You can think of this in many different ways, but obviously plus is going to push plus up. Minus is going to attract it upwards, right? Or you could say, which one needs to be at high voltage? Bottom plate. High voltage to low is the, okay. In this case, what else did I want to say? By the way, what direction is the electric field here? Yeah, do you agree that we've created an electric field that's upwards?
Yeah.
So just so it looks different, I'm going to draw that. We've got an electric field that's upwards now. All right, so far so good? Oh, it says determine the amount of voltage I would need, right? So right, let's say we know this, the size of this magnet from doing some experiments here. So we know the size of the external. We know the charge, the mass. I'm trying to figure out the voltage. What do I do? Relate the forces. Well, what are the equations for the forces? Okay, FE magnitude should equal FB, which is the same as what Christian was just saying. Agreed? The size of these two forces have to be equal, or right, you could say the vector sum to 0, and then one of them would be a plus j hat, one of them would be a minus. Good. So in this case, I want to just stick with the magnitudes. What's the equation for an electric force?
QE.
What's the equation for the magnetic force? We wrote it. I'm going to write it like this. Sorry. I'm gonna try and match the colors I used to. It's the same shit. Sorry, my bad. Sorry about that. I realized I was color coding it, and then wouldn't this one be? And then sine of some angle? Right, isn't that how the cross product works? First term times the second term times the sine of the angle between? Well, what's the angle between them? V is going this way, B is going out of the page. What angle is that? 90. What's sine of 90? Yeah. Is that helping? All right, what drops out? Whoa. Well, wait, what were we trying to find? Voltage. How do we get voltage in there? Yeah, how does voltage relate to parallel plates? Equation sheet on the back of the board. You remember that? What was it? Somewhere in there. Delta V over D. Aha. So now before we get there, I want to clean this up just so we can see this. E is equal to what? VB is basically all that's left. Agreed? And then from there, we could say, well, E is delta V over D, at least in terms of magnitude. All right. And then from there, do you agree we could solve for whatever we want? But notice something that we should watch out for here. This is one of those problems where we have an uppercase D and a lowercase d. You agree? So that matters. And then we see that in this particular problem, the amount of electric potential required in this case is dVB. Oh my gosh. dVB. Woo! So far, so good? Wow. What if you want a negative charge to do this instead? Everything's the same, but what if we wanted this to be an electron instead? Well, I should be careful, not an electron. We're told we want to just flip the sign, but keep the same mass and everything else. What's that? Would you? Let's think. What drops out in this problem? The charge drops out. My guess is we don't need to do anything differently, but let's think. If you put an electron here, or sorry, a negative charge of the same mass, what happens to the electric field and the, or sorry, what happens to the electric field if we use an electron? Anything or nothing? Nothing. This came from the plates. What happens to the force? That would flip. But what happens to the magnetic force? Still goes right through. Cool. All right. Interesting. What if you had a slower charge? What would happen to it? Let's say we were going a little bit too slow. If you're going too slowly, right? In this case, do you agree the force is exactly balanced? That's what the problem said happened. But what if you were going a little bit slower? Would the forces still balance? No. Which force is affected by the speed? FB. If you're going slower, what happens to the size of FB? It goes smaller. So if you go a little bit too slow, what direction would you be deflected? Up, right? The electric field is not affected, right? The electric field depends on the plates. So if you go too slow, you're going to gradually drift up. If you go too fast, you're going to drift downwards. It's almost as if only one special velocity is selected to go straight through. What is the one special speed that gets straight through? What's the one special speed that gets straight through? Isn't that cool? In this case, if the speed of your ion happens to equal the ratio of electric field to B field, it goes right through. What do you think? It's a little weird there, yeah. The units are crazy. We'll worry about the units later, all right? Yes, question, Angel.
As long as the ratio is kept, then it would pass.
That's right. So if you use twice the field of electricity, if you use twice the voltage, you get twice the electric field. You could then double the magnetic field and the same speed would still get through. Absolutely. This device has a name. Take a guess what it's called. It selects a velocity. It's called a velocity selector. All right. Now, what is the application? Is there any? Almost as if you're thinking about problem 28.6 on the next page. Look at 28.6 on the next page. We'll try and allude to that in a minute. But basically, stage 2 in that problem is a velocity selector. So more on that in a minute. That's a mass spec. Okay. All right. So far, so good. Now, in this case, did you see the mass pop up anywhere in here? No. But later on, we may learn that if you add in an extra stage, as is shown on page 28.6, with a magnetic field only, without the electric field, we can have the mass matter. And so we'll discuss that more. All right. All right, more on that later. Now, I wanted to show you something here. Pretty strong magnet, I gotta watch out. Give me a sec here. All right, you can kind of see that there. Give me a sec. Now, in this case, imagine I have, oops, I lost it. There it is. I have a switch here. Is this thing on? I'm gonna just crank it, all right? And then on Zoom, can you still see me, everything here?
Yeah, it looks good.
Right on, thanks, C. Now, I can plug this in because I've got this switch here. I don't have to worry about anything. I wanted to show you something here. All right, and then maybe I need something to hold this up. It's hopefully not magnetic. There we go. See, masks are great. This is why they require masks, in case you need something to hold your physics demos. All right. What I have here is a very thin strip of metal. It's aluminum foil. Do you agree that's like hella thin? Right? It's just like a few fractions of a millimeter thick. Now, in this case, what direction is current flowing? Can you tell? When I close the switch, I don't know if you can see the color code. Red is positive, right? Red, 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 red. So it's going to flow this way. Agreed? Now, in this case, I could take a DMM like this, and I could actually take this DMM and connect one clip here and one clip here, right? And the idea is it would actually look a lot like, whoops, wrong button. This actually looks a lot like that. Now you might not see it at first, but look at question 28.5 at the bottom. Okay, 28.5 at the bottom is similar, except do you agree I flipped the direction of the magnetic field there on the bottom one? In our problem 28.4, we had a magnetic field out of the page. In 28.5, the magnetic field is into the page, but it looks almost exactly like this situation that we see right here. Now, the idea here is, maybe what I'll do is I'll go to board 6 and show you the difference. In this case, imagine we have a piece of metal, and this is 28.5, I think I said. We have this strip of aluminum foil. There's current flowing this way. That's the current flow direction. Now, typically what happens when we have current flowing this way, what's actually moving inside the metal? Electrons. So do you agree we have minus charges going to the left? And do you agree for this problem, I told you there was a B field into the page?
Yeah.
What direction is the force on that electron? Positive J. Goes to no. B goes to B. So what direction is the force on the electron? Up, because it's negative. You flip it, right? Remember that? It's a negative charge, so you flip it. So doesn't this have a force upwards? Now, let's say right now there's no charges moving. Agreed? I haven't closed the switch. Right? Shit. Let me zoom out a little bit. I haven't closed this switch yet. It's still open. So in this case, as soon as I close the switch, do you agree current will flow? And do you agree as soon as current flow, there's going to be a force upwards? So we'd expect there should be a force, and I'll call it force B upwards. Over time, could you imagine some electrons piling up here? Like first maybe just one, then maybe two, maybe a few more, right? And so eventually we're going to get this. And as a result, maybe we get this polarization happening, right? Where there's a net effect of creating like a parallel plate type system here, right? Where there's an electric field pointed which way? We see this electric field is going this way. What direction is the electric force? Down. There's a force downwards. And what's going to happen is when you run this circuit, what will happen is fairly rapidly, you'll get a buildup of minus charge on top, positive charge on bottom. You'll get, whoops, this is a force electric. And we're going to get an electric force that balances this, and then the charges are just going to flow right through. This device, right? Well, eventually, do you agree we're going to get a voltage difference between the top and the bottom? That voltage is called the Hall voltage, and you could measure it with this DMM, except it's so tiny, we can't see it. So I got this here basically just for visual. The measurement is so small, it's always going to read 0, right? We're talking, and if you do the math on it, did I actually do the math? Does anybody have the solution up to 28.5 handy? If you want in part E, I tell you the actual numbers we expect. I think it's like microvolts or even nanovolts. So it's a tiny amount of volts, something, I think this only goes to millivolts, so I don't think we can see it. All right. It's microvolts. Yeah. So we expect when you plug in numbers in a real world situation, right? And you could actually put this DMM in here and measure the voltage between the top and the bottom. This is called the Hall voltage. And it's on the order of microvolts. It's a very tiny voltage. So we're not going to see anything here, but that's cool. So then I thought, is there anything we could do to make this effect visible and see the effect? So here, instead of doing this thing's so heavy we wouldn't necessarily see much. By the way, this Hall voltage is used in a lot of sensors, especially for magnetic fields. What you can do is you can calibrate this device and you can measure that voltage and work backwards and calculate the B field. And so you can actually use a Hall probe to figure out the size of the magnetic field. So if you're wondering how people measure magnetic field strength, it's something like this, only on a tiny little scale. And the trick is, the thinner it is, the better it works. At least this is what I recall. It has something to do with the thickness and current density and all this stuff. So basically, the skinnier or the thinner the film is. So what you usually do is you take a piece of semiconductor and then you use a very thin deposition of metal on top of it that's maybe microns thick instead of hundreds of microns thick. All right. If you want to know more, talk to Vince Tobin. He actually knows this stuff. All right. He's an expert at magnetism. All right. So now, in order to see this better, here's a variation on this. Right now, I have a current carrying wire. All right. Now, I want to use this as a way to detect which one of these is a North Pole and a South Pole. All right. So this is, what do we know about this circuit here? And can you see on Zoom? I forget.
It's slightly off center. There you go.
Is that all right?
Yeah, that looks good.
Now, in this case, by the way, I really, wherever you are, I really appreciate you being quick and helping me. It keeps class flowing. So thanks for all that work that you're doing and responding and blah, 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 whatever. Next. All right. What direction is current flowing through this wire when I close the switch? This way, right? Now, this is a horseshoe magnet. I don't know if you're familiar with these types of magnets. I don't know if this is going to show up at all, right? This is just a bunch of iron filings and some oil here. But when I put this in here, I don't know if you can see that at all. See how the field is really strong in between the faces? I don't know. Well, I'd take it out to show you, but I can't, right? Because the filings just keep going back in there. But the idea is you get this really strong B field right here in the center. And it's either going to be going this way or that way. And we don't know which, right? But we can tell it's either into the page or out of the page. Agreed? You guys want to play around with this? You can try this out. Pass it around. Those are some magnets. Now, let's get to our jumping wire. Okay. By the way, I tend not to put Hall voltage on a test, just so you know. It's a good practical thing to know. It was an experiment. It was good to think about, but I was more concerned in right-hand rule practice. If you're wondering why I didn't finish that problem, that's why. Got it? Is that clear? Got it. So just giving you a heads up. If you're like, why didn't you do that problem? Right? I like to practice the right-hand rule a lot. I don't know if you've noticed that or not, but I think it's crucial. All right, so now we've got a wire here. You guys just told me.
We're still looking at the magnet.
Thank you. We got a wire here, and we got this current flowing, and we think that the B field is either into or out of the page. And I think I just misspoke when I drew those, but this is out of the page and this is into the page, right? Dot means arrow coming out. X is feathers going away from it. All right. If the B field is coming out of the page, what is the direction? Well, there's a force equation for this. If we have constant current and constant B field, the equation is I, L, cross B external. And L points in direction of current flow. Current is technically not a vector, so we have to associate the vector with this displacement, right? So do you agree this would be the L direction? Right? Well, let's do the right-hand rule. It's always first vector goes to second vector, thumb is the output. First vector goes to second vector. If B1 was the force, if B1 was the correct field, do you agree it would be a force upwards? So that would be the direction of the force if the B field is out of the page. In this case, wouldn't it be the opposite? right? So now what you can tell me is when I turn this on, watch the wire. So again, we're going to turn this on and we're going to watch the wire and see which way it jumps. Ready? Also, this thing is cranked. I'm going to just show you this circuit really quick. Do you see any resistance at all in this circuit? No resistors. 15 volts. How many amps do you expect? A little? A lot? A lot. There's an overload meter. We're going to go for it. We're just going to break this power supply if we can. So now I can't actually close the switch and leave it closed. Watch the amps. Ready? And watch the wire. Let's see which way it jumps. Oh, which way did it go? Up or down? Do you agree it goes down? And then here's what's happening. After it goes downwards, it gets, there's a force sideways as well because the field gets warped once you go downwards here. But like this. Oh, did you hear that spark? Yeah. So it's clearly there's a force downwards. So what direction is the magnetic field here? B2. So what we just saw is because we got a downwards force, this was wrong. Nope. Yep. So now what you just told me is the field is into the page. Now I don't know if you know this or not, but in a typical bar magnet, there's a north and a south pole. Do you recall whether the magnetic field goes into south, out of north, or what do you know? I know. It goes out of north into south. So the idea here is, which one of these is a north pole? So we know in this experiment, the B field is supposed to point this way, right? So this is actually the same thing as that bar magnet. It's just really long and bent around in a horseshoe shape. If the B field points this way, this must be north, and this must be south. B field goes out of north and into south, out of north and into south. So north and south. Got it? More on that in the next chapter and the next chapter after that. Cool. And now I got to remember to erase this so I can make the next class have to figure it out. All right. All right. What was the point of this? I have no idea. Some directions of magnet. Okay, so basically we just use the right-hand rule to figure out a north and south pole. You could use something like this, the Hall effect, right? The Hall voltage to figure out the size of the magnetic field. So in theory, we could do all this. Another thing that you could do, you might be wondering, I don't know, how do they figure out electrons are the ones moving in here, right? How do we know electrons move in a piece of metal? Can't see it, right? If only there was an experiment that could determine this. Well, I'll just say it like this. The Hall effect, if you run current and the charges are electrons, the Hall voltage is one direction. And if the charges are positive, it flips. So the sign of the Hall voltage can tell you the sign of the things carrying charge in your circuit. Whoops, I was on the wrong board there. Basically, if you have plus charges moving this way or minus charges moving that way, that's going to affect whether your plates get plus or minus. And so that affects the sign of the Hall voltage. All right, enough on that. All right, so let's talk really quick about a mass spectrometer, which is problem 28.6. I'm going to leave most of this for you to do at home, but I want to kind of explain it. Questions from Zoom out there, anybody? All right. I wonder how many square feet of board I erase on average a day. When you consider I have to sometimes erase it 2 and 3 times. That's what my workout schedule is and keeps this lovely physique. Oh, sorry. That was too funny to me. All right. I oftentimes think about Karate Kid, wax on, wax off, as I'm going across. Old school. All right. What is a mass spectrometer? And this is 28 point what? 6. Talking about a mass spectrometer. All right. So, do you remember last time I had that $1,000 bulb, that light bulb, and it glowed? Right? You could imagine you have a hot ion source like that. Somehow you heat up a piece of metal or material or whatever, or you could use chemistry to do it, but somehow you create a source of ions. Okay. And just for right now, let's keep it simple so we don't have to think about minus signs. So somehow you heat this up and an ion comes out. And it's moving this way, but it's moving pretty slowly, very slowly, right? It might only be moving, say, like 1,000 meters per second as opposed to 10,000 meters per second or 100,000 meters per second, right? Ions should be going really fast. So, right, 10 meters per second would be nothing for an ion. If you want to speed something up, what do we do? You get a plate like this and you put a hole in it. Then you have another plate here. My attempt to draw this with a hole in it. And the idea is the ion can drift through here. And then once it's through there, you can make this plate positive and this plate negative, right? And so now keep in mind, if you have a positive plate and a negative plate, there's a strong electric field in between. What's the electric field outside? 0. So we don't have to worry about this plus plate pushing this thing away, right? Because the minus plate is canceling out that electric field as long as the plates are huge compared to the distances, right? If the plates are approximately infinitely large, this thing's going to come through here, go through the hole, and then what's going to happen is there's going to be this huge electric force inside. And it's going to speed up. So it's going to come out of here going much faster. What's the name for a device that speeds something up or accelerates it? It's a particle accelerator, right? You accelerate the particle. Piece of cake. Now here's the issue. Do you agree that these hot ions are going to come out of here at wildly different speeds?
Yeah.
And so small differences here, we might get all kinds of different speeds coming out of here. So then maybe what we'll do is send it through a velocity selector. Right? And things that are going too slow will get crapped out. Things that are going too fast will get crapped out. And so then maybe what I'll do is I'll put a plate here and have a little slit. And the idea is anything that's going even slightly too fast or too slow, it doesn't even have to get all the way down there. It just has to hit the edge of this, and only a very small amount of velocities will get through. So we'll have focused the beam, like the focus knob, right? Now remember, to do this, let's read this particular one. Hold on, stage 2. Stage 3. Oh, okay. So we're going to have to do some thinking here. But this thing's coming through here. The velocity selector doesn't change the speed, right? So we got this plus ion here. And now it's going to go in a circle. What type of field is present in this region 3? It's got to be magnetic. What direction is the magnetic field? Probably. What direction does the force need to be? At this spot. Towards the center, right? So we know there's a magnetic force here. So now V goes to B goes to there. Now we could be saying, well, wait, you could have a component this way, but actually if this goes in the full circle, the only way that's possible is if V is purely out of the page. I don't know if you remember that. If things go in circles, there was no stray components. If there's a weird component, remember we got the helix instead, right? So if this is going to move in a circular path, we don't have any helical motion, we know that the B field in this case is, what was it? Out? Well, we're told there's the same magnetic field over here. What direction is the magnetic force in the velocity selector? Same way, right? So what direction do we need our electric force to be? So what direction does the positive plate need to be? Or which plate has to be positive? So this has to be the positive plate. This has to be the negative plate when we're applying voltage. Right? Now in the end, let's look at the force equation here. I don't know if you remember, but QVB, I'm going to ignore the sign of 90 degrees, right? Because there's really a sign 90 here, should equal MV squared over R. Remember when we solved this for the radius the other day? What do you get? The radius is equal to MV over QB, which depending on who's solving it, some people say it's V over B times the quantity 1 over Q over M. Or if you're a weirdo chemist, what do you use, Jesse? What's that? Oh. So this is called the charge to mass ratio, right? And sometimes organic chemists will use the mass to charge ratio. Right? Is that what you call it? Yeah. So I can't help it if something's wrong with chemists, because clearly this is a much more efficient way to write this. Anyway, but I just want to point out, do you agree that the size of the circle will depend on not only the charge of this thing, but also its mass, right? Now, we can control the velocity by adjusting this B field. So you can set the velocity, right? The B field, I don't know if you remember, the velocity, wasn't that something like E over B?
Yeah.
So the idea here is the radius will depend on the electric field and magnetic field you choose and the charge to mass ratio. Now, what happens here is this is the worst mass spec ever. Give me a sec. The idea here is this. Can you guys see this on Zoom or not? Let me switch it up.
Yes, now we
There you go, yeah.
All right, this is a very cheesy version of a mass spectrometer. There's a really big magnet here, and now I've got this really big one, and just to be clear here, right, this is clearly, oh my gosh, that's a strong magnet. Now what I'm going to do is I'm actually going to put this strong magnet under here, and this little one, whoa, that's just to hold it in place, all right? Now, here I have several objects. The idea here is, now, I guess I'll show you like this so you can see. The idea is this is like your accelerator stage, right? Here it's old school. Your gravity is the accelerator here. Then there's this magnetic force, which is causing different radii of curvature, depending on which size spheres I use, right? Can you see those spheres at all? Yeah. So I have several different spheres here, different sizes. Maybe now you can see them a little better. And the idea here is when I run this thing, oops, I need to move this a little closer. Let's try this again. All right, so here we go. And we can see that the radius through which it turns is different depending on the size mass you use, right? So this one's probably going to get stuck. But again, so I can't really show you this because I can't turn it. But the idea is here, this big one's going to come down here and kind of go into one of these closer holes, right? And then this slightly smaller one with a different charge to mass ratio might be able to deflect in a different path, and it's going to fall into these different bins, right? And so the idea here is you can make a computer count all the different impact locations. And so you can tell how many ions of this charge to mass ratio were in there versus this one versus that one. And you can tell what's inside a material by looking at this pattern, just like a fingerprint. You can think of a spectrum as being like a fingerprint, right? It identifies a material. You can identify how much toxic sarin gas is in something, or how much TNT or whatever, right? So you could use this to detect toxic chemicals or just normal chemicals or any chemicals. All right. Good on that? Pretty cool. Let's take a break. Is it time? Oh, it's 5:30? All right, maybe we should keep going. Do you guys like it to push farther before we take the break so the end is fast? Is that cool? You guys? Christian, you good with that? All right, all right. So anyways, just out of curiosity, was it worth me dragging the stupid thing over here or not? You guys, that helps you guys see it?
Yeah, that was cool.
It's, man, it's a lot of work. Student built this for me. Yeah. Back in the old days, when one of the labs would build me something I don't have. Yeah, that was a tough lab. Did I tell you guys about the one student, their job was to collect sand for 10 hours? Yeah, right. All right. Okay. Let's get back to it. All right, so let's go back to here. Now, we kind of beat that to death. There's a really cool problem on 28.9 on page 142 in my book. Think how easy this would be to code this type of stuff. Maybe starting not this Thursday, not tomorrow, but next week, some of you might be really into this, and we have a 3-week project coming up. Maybe you would want to do something like this, or maybe I had a student one time, they made a simulation of a mass spectrometer, right? And you put in all the voltages, and if you want, you could go online and look for one, and you kind of get an idea of what it might look like. But in this case, we could talk about that more in lab tomorrow. So some of you might be able to do this as a coding project, and you could give a talk about it. All right. That cool shape looks like a Brachistochrome, which, you know me, I love my path of least time. That's such a weird problem when you think about it. 28.9. I just love that problem. Moving on. I want to talk now about problem 28.10. Oh, I just turned it off. Okay, 28.10. To give you we just looked at this force problem, right? And it's this problem again, where I have a wire inside of here. This problem is shown on page 143 in my book, 28.10. The idea is you got a wire carrying current. And then there's this magnetic field. And I don't know if you saw this at all, but remember the field is really strong here in the middle and it gets weaker towards the outside, right? That seems reasonable. Well, look at the equation in 28.10. I'm going to write this up. So again, we're trying to simulate this problem of just force on a wire and understand it a little bit more exactly. Okay. So go ahead and read it and get a head start reading it. If you want, read the top of that page too, where I talk about magnetic force and integrals. I wonder if a smart board would be faster, but I hear they're really glitchy, right?
Yeah.
I just don't trust markers work. Yeah, it's like simulations and video clips. Things can always go wrong with them, right? Markers work. Stick in mud always works. New markers. Intense. I like it though. They're showing up well today though, right? That's what I like. Okay, so we've got a wire here. What did I say, 28.10? Thank you. Got a wire here. Am I on the right board, Zoomers?
Yeah.
Thanks. Right on. Okay. So now in this case, we have a strong magnetic field. It doesn't matter which way it points, right? We could do a different problem later, but the idea is this is supposed to be just like this magnet that we see here. It's strong in the middle and weak as you go outside of it. That equation that I wrote for it, I don't know if you saw that. I said B is some constant, B naught. Was it in the K hat? Yeah. Now, I guess I should be clear here. There was current flowing this way. There's current flowing this way. And then there's a coordinate system kind of drawn here where it's biggest in the middle. So we're setting our coordinate system right in the middle where the wire is right in the middle of this thing, right? And so this is supposed to be our little wire here. It's kind of blown up and zoomed way in, right? Before we get ahead of ourselves, does this magnetic field equation make sense? Where is it going to be biggest? Yeah, when x equals 0, the denominator is as small as possible. As x gets bigger, either positive or negative, you see it's going to fall off?
Yeah.
If you plotted this, do you agree it would kind of look like this? It would get smaller as you go away, and eventually as x gets really big, wouldn't it get close to 0? This actually relates to a famous curve called the Witch of Agnesi. If you want to learn more, talk to me after class about the Witch of Agnesi or the trisectrix of Maclaurin. All right, whatever. Named curves are really fun, but it doesn't do us any good. Now, in this case, this seems like a reasonably B field, strong in the middle, gets weaker on the outside. We have a new equation, right, for figuring out the force. The force is going to be the integral of I ds cross, let me emphasize these parts right here. That's coming from the current. IDS cross B external. I'm getting spicy. Taking the caps are off, fools. The caps are off. We're getting serious now. All right, so in this case, B external is pretty self-evident. The issue here is, normally, if you recall, our old equation was force equals I L cross B. Well, if the B field is changing, the idea is we just need to add up all the different contributions. So at this length of the wire, tell me the B field. At the next segment of the wire. So what we're going to do is we're going to split this thing up into chunks. Right? This is only valid if B is the same everywhere. If B is uniform, that's great. If B is non-uniform, we use this. What does ds mean? It's a small chunk of the wire. What's a good name for this small chunk? dx. What direction is it? I hat. Remember, it's the direction that current flows, even though current is not a vector. So in this particular problem, ds vector is equal to dx in the I hat. Everybody okay with that? Now, in this case, going back to problem 28.10, do we know how long the wire is? It's okay. It's a wire of length L. I'm going to assume it's centered on the origin. Does that look like it's centered to you? Maybe I didn't say that. So let's say total length equals L, and let's assume centered, even though it doesn't say that. When I do this, how does that relate to this integral? What's that? The bounds or the limits. So let's put all these pieces in here, right? We're going to get an integral. What are the limits on my integral? Negative L over 2 to right. The total length is L. If this is 0, wouldn't this be negative L over 2? IDS, I is a constant, isn't it? Right? Think about it. In most wires, we have the same amount of current in each piece of the wire. Fluid in equals fluid out, right? So we have the same current. And then ds is now dx in the I hat. And what is our B, this big ugly blob? Now, you don't have to listen to me here, but I highly, highly, highly recommend it. In general, when you see a cross product inside an integral, what do you think you do first? The integral or the cross product? Cross product. Now, if you get that on lock, you're going to be in good shape for some of the stuff we do in the next few chapters. Always do the cross product first. The big benefit is oftentimes, if you do the cross product, sometimes you get 0 and then you don't have to do the integral. Other times, you might get partial cancellation from the, okay, so it's crucial to do the cross product first. So let's do that. What do we get from I cross K? No one can remember, so we draw the wheel of whatever. By the way, no one else calls this the wheel of pain, only me. What are we doing? I cross K. What do you get when you do I cross K?
Negative J.
Negative J, because we're going the wrong way, right? So this is negative J hat. Now, negative J hat is a constant. I can pull that out. What else is a constant in there? Probably BO and L squared. So now we can rewrite this integral and make it look a little bit prettier. We're going to get 4 subscript B equals I B naught L squared and the K, oh wait, negative J hat can pop out, right? Times the integral of some stuff. What's that? Dx over. Got it? How would you attack this? I like what you're doing. What is Christian doing? Looking if it's on the table, and it is, right? So you could do this with a table. You could also do it. What other math technique might work? You could do a trig sum. Could you do partial fractions with complex number theory? Probably, right? I think you could do partial fractions on this one too, if you use complex number theory. But there's one thing I want to ask here, right? Do you agree that if we could use 0 as one of our limits, it's a little bit easier?
Yeah.
So it's always worth checking, is this one of those problems where we could change this to 0 to L over 2 and double it?
Yeah.
You say yes. Why do you say yes?
Show us the graph of the symmetrical element.
Ah, excellent. I don't know if that's good or bad. The most disturbing part is you think like me. So that's something wrong with you. All right. But so what I think about is when I think about the graph, isn't the integral the area under the curve? So if it's symmetrical, this always works for me. If I think about the shape of the graph, if the graph is going to be symmetrical, then I can do the trick. The other way is, what types of graph are symmetrical? Even, not parabolas, evens. Parabola is one of them, but so is x to the 4th. So is x to the even power. So even functions, like this one. It's got x to even powers, right? Now, yeah, but for me, I still am a little bit hesitant because I like to look at the graph. So if you're not sure, whatever. And let's be honest, in the real world, how are you going to do this every time? Wolfram Alpha and make the computer do it, right? As you get higher and higher up, you don't have time to waste time on this nonsense, so you make a computer do it. Now, that said, what I do is I give you a table for this class, and that's like kind of the trade-off. You're still learning, supposedly, right? Whatever. All right, so in this case, you could actually double this. If you remember to set the limits right. At this point, this is just math. I'm leaving the rest for you, but it's a good problem. All right, what do you think? We're actually cruising right along. I'd like to do one more problem before we take the break now. All right, any questions on Zoom out there? Getting it?
Sorta.
Okay, I'm gonna erase the other board. You guys can take a second to make sure you get all your notes down or look up the solution or finish that problem if you want. It's gonna take me a minute. And we're gonna move on to the next problem in a minute, which is 11, 28.11, so. Isn't this stuff fun? Yeah. I love this stuff. I'm a glutton for magnetic punishment. It's just so interesting to me. Why? But I love it. It's just gonna be cooler too. I don't know. This is some fun stuff. All right, what am I doing here? Changing the board, I think. 6. 28.11. Now to give you an idea here, this is not exactly a loop of wire, but imagine if I had a loop of wire that's kind of in this shape, right? So you can imagine now these marks are kind of indicating the loop of wire. We're going to use this as our visual aid. All right. So we have a loop of wire here. Maybe I'll do. Okay, the current is counterclockwise in that loop. Yes. We got a half circle. It's not perfect, it's pretty close. And then what's a good spot to put the origin of a coordinate system for a circle? At the center. So for a half circle, that seems pretty good too. So I'm going to do that just right now. I don't know if you noticed, with magnetism, it's crucial to understand your coordinates all the time. Always understand your coordinates. So I'm going to actually take the extra effort to label it. In this problem, there's a B field this way, is that right? Did I draw it correctly? Yeah. All right, so is it constant or not constant? Did it say, is it uniform or not? Yeah, uniform. Uniform magnitude VH10. Okay, so the magnitude in this problem is V, and it's in the I hat. I should write an EXT, but I'm lazy. I just want to get this done. Okay, so it's some magnitude to the right. Got it. And then current is flowing this way, which means current is flowing this way, this way, this way, and this way, right? That's supposed to be the current. In this case, our goal is now to figure out the net magnetic force on the loop. Agreed? So we're trying to get the force. So this problem was pretty arbitrary, where I had just a single wire segment, right? Well, that was okay because it was going through this. But a lot of times what will happen is you actually want to put the entire loop inside of there, right? So you want to have the entire loop inside the magnetic field. You can imagine wrapping that up really tiny and sticking it in the magnet. All right, so in this case, there's two different segments here. Maybe we'll number them. How about this bottom one? We could call this segment 1 and this upper one segment 2, just for no good reason. Yeah. Now, for segment 1, we've got a uniform B field. Couldn't I just get the force like this? For segment 1, that's just going to be I, L, cross B. Agreed? Because it's a uniform B field, I can use this formula. All right. More on that in a minute. I guess, do you agree the length vector is also constant? Yes. This is the bottom part of the circle. Yes. So it's this is 1. This entire thing all the way over. Yes. Well, what's the L vector in this case? This circle has radius R, right? Yeah, this would be 2R, that's the length of it, in the I hat direction because the current's flowing I hat. What's the external field? What's the force? 0. Do you agree? No need to do calculus. In this case, because I hat cross I hat, good. So the force on segment 1 is nothing. Now all we have to do is worry about this one. Now here I want to be a little bit careful. So I need some space. I'm going to need all the space I can get. So what I'd like to do is erase this and just write it right here. Force on segment 1 was equal to 0. We just figured that out. All right. Now, in segment 2, this curved segment, here's where it gets tricky. You might think I don't need to integrate because B is uniform, but in this case, L is what's changing. Do you agree the L vector is changing directions at every segment? So now we have to write an integral even though B is uniform. So I know there's going to be a current. I know there's going to be a cross product, actually. And I know there's going to be B in the I hat sitting down here. The question becomes, what is ds? We need ds, right? What does ds mean again? Physically? A small slice of the wire. Let's look at a small slice of the wire here. That's ds, a small slice of the wire. And again, we're looking at segment 2. We already took care of 1, all right? It's a small length going around in a circle. What is it? It's not your d theta, it's our d theta. But that's not good enough, is it? This is not a vector. We don't know what the cross product's going to do. What's a good name for around the circle the normal way? No. Theta hat. So let me do a quick coordinate system here.
This is what you're going to do there.
Yes. This is an R vector, right? This is a tiny bit of angle. That little angle in there is d theta. This little length is r d theta. But now the direction is, well, this is sometimes called the r hat. This is sometimes called the theta hat direction around the circle. Right? So in math class, we normally think of that as being theta. So we're going to think of this as being theta hat. Now think about it. You're going to see me do this a lot. My thumb is like the pivot point, and the tips of my fingers are showing you theta hat, right? This is the r hat. These tips of the fingers are the theta hat. When I'm right here, theta hat straight up. When I get to this point, my theta hat's this way. Theta hat's down. Theta hat's towards me. Right? So now I'm going to call this theta hat. From experience, I know this. Theta hat is equal to negative sine theta in the I hat plus cosine theta in the j hat. If you want to know more about this, talk to me outside of class. For now, I just want you to memorize this is the standard theta hat. It's written in the problem statement. Got it? I'll show you later, but whatever, not now. Okay? We got to get this problem done. Well, we still need a little bit more. This is not a complete integral. I'm not quite ready to turn the crank. What have I forgotten to do? Limits. Okay, I heard 0 to pi. We have to do theta in radians for this equation to make sense. So I can't go 0 to 180 degrees. I got to do my 0 to pi, right? Here's 0 degrees all the way over to pi. Cool? Now, that was a lot. I'm going to pause for questions. Did any of that make sense, or any questions, Zoom or otherwise? Yes, go for it.
So if we're integrating radially outward, then we use R hat for R.
Yeah, so if you had a radial, like I technically right here, do you agree you could go radially outwards? And here you could go radially inwards? But that's not worth it.
Right.
X and Y are easier. Here's the thing. I want you to notice something here. Is theta hat a constant? It changes as you go around, right? Theta hat changes. So the issue is you can't just pull theta hat out of the integral, can you? This is the other reason I told you always do the cross products first. Because if we do the cross product here, what's going to drop? The I hat part of theta hat will drop. Then we're going to get the J hat cross I hat, and then we have cosine, and we got something to integrate. Do you see it?
I see it now, yeah.
Yes, Angel.
So I had a question then, because when, before I left, we were talking about negative and positive, from clockwise and counterclockwise.
Yes.
In this situation, it would be.
So we would say counterclockwise is positive theta hat. Clockwise would be negative theta hat. And so this is a way to kind of generalize the clockwise and counterclockwise directions. Excellent. Good?
Yeah.
Nice, nice. Hey, plug some stuff in, will you? Race you. Go. Beat me. You can. Or was there another goal? Get this integral before I did. I guess we could factor out some constants. Now, since this is Santa Maria, we got to get some barbecue involved in this equation. This is my famous barbecue calculation. Why is this the barbecue calculation? Because you get ribs. Ribs. If you're vegetarian, I meant tofu ribs. I make a mean tofu. I don't really like it, but my rest of my family keeps making me make tofu all the time. So I got my special tofu I make. All right, so now I gotta figure out what the heck's left. Shoot, okay, so the ribs pop out. What do we got left? We got a d theta, that's still in there. We got a theta hat cross I hat. Now to save time, I'm just gonna say this term drops, so all I get is cosine theta J hat. Notice the order matters. The theta hat has to come first. Yep. So what's J cross I? Negative K? All right. Turn the crank. I'll meet you at the end. You're gonna laugh here. You're gonna laugh when you finish, right? Did you already finish? What's the answer? Yeah, what? The answer is 0. This is like the longest calculation gets 0. But it does give us ribs. All right, we got those ribs. So I got a rib. When I integrate, oh, there's a minus K hat. I'm just gonna stick that right there. And then we got the integral of cosine is sine or negative sine. I'm never sure. So what I do is I just say, okay, let's just try sine. Well, when I take the derivative of sine, I know the derivative of sine is positive cosine. Got it. So I always check it that way. So we get a sine theta evaluated at 0 and pi. After all that, you get 0. You want to hear something funny? The integral of the net force on any loop in any uniform magnetic field is 0. This is always true. But I want to go a little bit further in this. I want to look at this using the right-hand rule. You know me, if I can't get my right hand in this problem, it's not worth doing. So here, let's go. What direction is the force here? They're parallel, no force, right? What direction is the force right here? Just for this segment. I goes to B, goes to into the page. Do you agree? Up here, there's no force, agreed? Anti-parallel. How about over here? So this is a little bit sneaky. What's really happening here is there's no net force. Well, what's happening is this side's being pushed in, this side's being pulled out, right? It's almost as if there's a torque. Yeah, it's gonna hurt. You know it's gonna hurt. But so here's the deal. There's no net force, but there could be a torque. What is the application of running a current through a loop of wire and getting a torque? A motor. That's what this is. This is the world's crappiest motor that you're going to build tomorrow. All right. So if I could zoom in on the idea here is you could take a large magnetic field. Now this is not quite right, but I don't know if you can see this at all, but there's a loop in here, right? So you take a loop of wire and you're going to get a torque on it, and this is going to twist, right? So if I go back to my big picture, there it is. The idea is if you, damn, that hurt. Oh, that's my axle, right? So you can have an axle here and you can make this thing spin around. But what's the problem? Think about this. The current is currently flowing that way, right? So I'm just going to point this out. There's a current flow that way, and I'm going to write the same thing on the other side. Right? Same thing on the other side. So the idea is, when it turns around, what happens to the current direction? It flips. So then what's going to happen to this thing? It's going to turn into this terrible motor. So the trick in any real motor is you have to build in what's called commutators, something that somehow allows this thing to change directions. And we'll discuss this more in lab tomorrow. If you're wondering how this works, let's deal with that in lab. Sound good? All right. So this is a good time to take our break. What we'll do when we come back is we'll do the torque calculation and learn about this. Now, I do want to point out, I didn't do any of these other cases. I just told you some facts. So let's write down the facts we learned before we take our break, right? Is that a good idea? Yeah. So some facts. Fun facts about magnets. Okay. So one is.
We're still looking at the motor.
Thank you. So one fact we learned was theta hat can be written as minus sine theta I hat plus cosine theta j hat. That's a fact. Number two was net force on loop in uniform B external equals 0. However, torque does not equal 0. In particular, and I'll get your question in just a second. We saw that we get a torque if the B field is in the plane of the loop. Now, I didn't do this one for you for case B, but when you do that one at home, you'll see that the forces are all radially inwards or something like that. Angel, you had a question?
Oh, is this, what the UD?
Oh, uniform.
Oh, okay.
Let me write that better. If I would say the word like this, right? The force is 0. Maybe I should have put it right there. There, that reads better. Net force is 0 on a loop in a uniform external field. Cool? Break time. Oh. Yeah. we'll see, right? So I think it's good like that to see different kinds of instruction.
If you have enough GPUs.
So hopefully that's a positive in your transfer experience. Yeah. I hope so. We'll see.
Yep, and power and everything. So 10 GPUs will make about like $35 a day, roughly about 67 XPs. Roughly, if you're mining Ethereum.
Getting pretty
You
close.
just said this.
Cryptocurrency is that gold rush right there.
There's a strong magnet. I actually have 3-inch pull faces in the lab, but I'm too scared to put it together. Because I would literally crush my finger and it would- yeah,
Wood.
right? Yeah, I mean, these are pretty strong too, right? Like this is. What's that?
Right. Like this is.
I don't see it.
If you come into here, right, this is gonna be kind of. Right? So you gotta be careful with these big ones.
Start doing the bicep curls.
I had a student once carried a 200 or, no, I think it was a 500 kilogram steel, no, iron mass. And they got a big gash in their hand because it was so powerful. It just slammed their hand in there and cut it wide open. There's blood everywhere. So you do have to be a little bit careful with these. They're no joke. These neodyms are so powerful. You know, I'm gonna get a little spicy on you guys here. I'm gonna pull the, don't write anything down for a minute. Okay? We're gonna get back into it. And I want to look at page 144, problem 28.13. Which board am I on? I'm on the wrong board. Okay. So again, I don't know if you heard me. You've got the solution to problem 28.13. So you can review it later, but I also know from experience, we're never going to do this type of math again. We're going to derive a result and then use the derivation to do. All right, I'm just going for it. Ah. All right, Mark. Are you the good one? 28.13. So here's the deal. We're trying to understand torque. This problem is all about that. So there's a lot you can learn. So you should just watch. And remember, if you want to have the solutions open on your phone or your device or whatever, that's cool. Are we on the right board? Yes. So now I have a loop of wire here. This looks disturbingly like the motor wire that you're going to build tomorrow, the loop of wire. Now, it's a single loop. So sometimes what I'm going to do is N is the number of loops that I use. To be clear, I just use the wire and went around one time in the rectangle instead of 20,000 times or something. Okay, so that's why I'm saying N is equal to 1. In this case, the current is flowing this way, and this way, this way, and this way. Right? In addition, there's an axle in here. And to be clear, it's trying to show you this little thing here, this motor here. And I know this is kind of a small version of it, but see there's a rod here. And the idea is I can twist this thing. And I don't know if you can see it, so I'll zoom in really quick. The idea here is you can twist it and you can see it twisting. So there's this metal rod and it's free to twist about that. Got it? Good. Now there's a B field flowing. Let's just say there's a B field this way. Not flowing, but directed that way or whatever you want to call it. The external B field, we're going to say is just B in the I hat, okay? Now, I want to learn about the torque on this loop. To learn about torque, let's first remind ourselves of the force. And in particular, I think I labeled these, didn't I? A,
Yeah.
B, C, D. Oh, not C twice, that's a D. So which wire segments, for example, AB, BC, CD, or DA, experience no force? Which ones have no force? I'll remind you of the
AB and
force
CD.
equation. Okay, just a second, hold on. It's I, so we're gonna get Jacob's answer here in just a second. Okay, say again, Jacob.
AB and CD.
AB is parallel.
Right.
CD is anti-parallel. Those have nothing. So we just told force AB equals force CD equals 0. So to be clear here, what I mean is this is the force from segment AB. Cool? All right. Now, what's the force on this wire segment going to be? I guess let's call that force BC. Well, there's going to be an I. Oh, what are the lengths? Do we know the dimensions on this problem? I think we do.
Height H with W.
So this is going to be width W. And this is going to be height H. All right. So let's plug in all the pieces. I is the current. There's going to be I. What's the length of segment BC? H. What's the direction of it? Negative J hat, because it's the same direction as current, crossed with B in the I hat. What do we get? Let's see, I goes to J goes to K hat, so J goes to I goes to negative K hat, and then because there's a negative, I think you got it right. So I believe out of all this, it's going to be HIB, or whatever, H, I, B, K hat. When we get the answer, we could check with a right-hand rule. Agreed? So far, so good. Well, what do you think is going to be true about force DA, the only piece left? Okay, everything is the same except for the current, so that's going to flip this. And then we're going to get negative HIB K hat. Agreed? All right. So according to this, it's going to twist, right? And so we're expecting, oh, I need a, whatever. Here's my loop. Just pretend this book is the loop. There's a force out of the page on this side, a force into the page on this side. So we expect it to twist like this. Agreed? So we kind of know which way the torque is already. But let's figure it out and derive it. Does anybody remember? And so I guess to be clear, this is the axis of rotation here, right? What was the equation in general for torque? He said torque equals I alpha. That's true, but I don't want to go that way. Because I don't know the angular acceleration. I don't know the moment of inertia. That's a valid equation. This is Newton's third law in torque land, but that's not where I want to go. How do I figure it out from the force? R cross F. Outstanding. Remember that? Now, we don't have to worry about the top and the bottom segments. Do you agree? But we do need to figure out what this R vector is. Do you remember what the R vector was in torque land? From what? pivot or axis in this case to point where force applied. Can you guys see that, or am I too low on the board? You can see it? Okay. Well, in this case, let's get the torque for segment BC. All right. The torque for segment BC, I need an R vector from the axis to the point where that force is applied. What is the name for that R vector in this case? W over 2 I hat. We're assuming the standard coordinate system. To be clear, we're assuming this is I hat and this is J hat, right? So you just said W over 2 I hat. Then we're going to cross that with the force, which was this one, HIB K hat. What do you get out of all that junk? Just making sure. HW, I drank your milkshake. That's my reference to one of the characters in There Will Be Blood. Remember that movie? Whatever.
It's a good movie.
HW, this is my son HW. All right, next. What direction was it? I goes to K goes to, wait, what is it? Negative J? So far, so good? Well, what do you think we're gonna get for the torque due to segment, what's the other one? DC. What do you think? Same or opposite? Let's do the math. What's the R vector? Ah! Negative W over 2 I hat. Cross, what's the force? Negative. Oh, HW. Do you see the minus signs cancel? We get the same answer because the minus signs cancel. I still get I cross K. I get the same exact answer. What's the net torque? Wait, what is HW other than a character in There Will Be Blood? The area. You just told me area times current times B field. And then there's a direction, negative J hat, equals the torque. That seems like too much of a coincidence. Wait a minute. What if I shifted this axis a little bit this way? Would I still get the same result, or is this an artifact of being exactly in the middle? What do you think? It works. If you go over here, this one gets longer in exactly the same amount that this one gets shorter, you'd get like 2/3 plus 1/3. It would still work. This result is valid no matter where you put the axis. And so what we're going to do is we're going to write this in a new way. And that's the next problem here. Well, let's go to the next board here. It turns out there's a general way to write this. Mu vector is called the magnetic moment. Yes, Jess. This is the same magnetic moment you discuss in your chemistry classes. Yeah. So this is the magnetic moment. In general, it's actually N-I-A. Now, we need a vector here. N is the number of turns. Is that going to be a vector? How about current?
No.
So what does the vector have to be? Is area a vector? Yes, right? The area of the surface was perpendicular to it, right? So remember, we had a current loop here. So I could have several turns going around, maybe N equals 3. And then this would be the area, right? It'd be pi r squared divided by 2 for this one. And the area vector would be whichever way the loop is oriented. Cool? So that gives us this new thing. The torque is equal to mu cross B external. And that's valid, whether you're doing chemistry or whether you're doing physics or whatever you want to do. There's another cool thing that we could talk about. Energy. Right? We've talked about magnetic, or we talked about electric field energy. We could also talk about magnetic field energy. In particular, it's mu. Energy is a scalar. Instead of a cross product, I would probably use a dot. But here we have to be careful. This is not right. There's a giant minus sign here. And I want to explain this. I don't know if you can see these red and blues, but I want you to think of this blue as being the external field, like this is a magnet. And this would be a current loop. If it helps, I'm literally doing the same thing as if I had two magnets here, right? Well, here is the lowest energy state. Do you agree these magnets are aligned right now? Now think about this. If the magnets are aligned, if mu, like think of mu as like a tiny little magnet. If mu and B point the same way, the dot product is positive and you get a negative answer. What if they're pointed the wrong way? It's hard to push them together, right? There's potential energy there. If I let go of it, what's it going to do? Flip. Whoa, that's spark. Did you see that? That was pretty cool. Let's try it again. So again, I purposely flipped it the wrong way. There's a lot of potential energy here. You can actually cause it to flip. I better be careful. Okay. Now in this case, the idea is like this. Mu is like your current loop, and a current loop acts like a little magnet. And this is like the magnetism associated with that current. So depending which way you have a B field, take a look at this. If they're pointed the same way, do we get a torque? No, the cross product is zero. They don't want to flip. If you're perfectly pointed opposite, we shouldn't get a torque either. But what happens is, what if you're ever so slightly off? You could get a torque, and that causes them to flip in a line. Now, in this case, if they're pointed opposite ways, we're going to get a large negative answer here from the dot product, which gives us a large positive energy. If they're aligned, this is the equilibrium state, the lowest energy state. This is actually how much energy state, if they're at right angles. Dot product measures how parallel they are. If they're perpendicular, what's the dot product? Zero, cosine of 90, right? So this is negative energy, zero energy, positive energy. So as this thing gets into better and better alignment, the energy becomes more and more negative. That's like saying this, when you raise this up and then let go of it, it's getting to lower and lower energy states, right? So the idea is this minus sign actually makes sense. The torque equation makes sense with how much it wants to rotate, okay? Once you get this thing started, it's going to go more and more to a right angle, and then here you're going to get maximum torque. When things are perpendicular, you're going to get a maximum torque. So the idea here is right? So if you have a current loop in here, whoa, oh, there's something magnetic in here, all right? Here's a current loop, copper, right? So the idea here is you could have, can you see this on Zoom at all?
Probably should zoom in just slightly. Yeah.
All right. You got a copper loop here, right? The magnetic moment is basically if your current is flowing this way, grab the loop with your right hand. And that says, okay, if current's flowing this way, my magnetic moment's that way. If the current's flowing the other way with my right hand, It's flowing into the page, right? You guys kind of see that? So that's how we're going to figure out the direction of mu. Just curl your fingers around. I'll write this down in a minute. But now when I do this one, if I put this thing in here like this, right? The B field might be up. The magnetic moment could be out. Right? If there was current flowing through this, this would flip. And here's the deal. How do you know which way it flips? I cannot emphasize this enough. This is a good way to remember it. Right? Mu tends to align with B. Remember, I've been saying that for about the last 5 minutes. So if you're not sure which way it's going to rotate, just think, what direction is my mu? Which way would it want to go? This way. It wants to align. Cool? All right. See this how dangerous this is? Just grab those scissors. All right, so now the idea is let's look at problem. Look at 28.14. I'm going to redo it. The same problem using magnetic moment terminology. Okay. We've got a loop like this. The current was flowing this way around the loop, right? So now, in this case, what direction is the magnetic moment? Grab your right hand, curl in the direction it's flowing, right? So notice, I'll write this down, direction of mu. Curl fingers of right hand in direction current flows. Right thumb points in direction of mu. Got it? Into the page or out of the page for this one? I've already forgot. Into the page. Okay, so mu is into the page here. Got it? What direction was the B field? Was it this way? If I want the torque, equals mu cross B. In this case, mu is the number of turns times the current times HW. In this case, what direction was it? I just forgot. I think, did we assume the standard coordinates where we're assuming this is I hat and this is J hat? So it was negative K hat. Crossed with B was something in the I hat. Isn't that a lot easier to do than all that work on the other board? So that's why I was telling you to tune out on that. You derived it, you kind of understand it. We'll learn more about it. Okay. That's it. Yeah. So now the question becomes, we need to do some problems where there's like a net force on it, right? And a net torque and figure this out. So let's see if there's any other parts of 28.14 that are worth talking about. Okay, do you agree we did part A? This is part A. That is the magnetic moment. Part B, the torque. Let's just crank that out. What do you get? Minus J hat, right? Do we get the same result as before? I hope so. Yeah. We better. What was N in this particular case? 1. So that's where the N goes. But so I'm just going to write it N I H W B. What was this? Negative J hat? What the heck does negative J hat mean? Wasn't there an axle in here? There's an axle running through here, right? This is the axis of rotation. Take your right hand. Grab that axle. Grab it in such a way that your thumb lines up with the direction of the torque. When we say torque in the negative J hat direction, that just means it's rotating about the negative j hat axis. So grab that axis and look at my thumb. Do you see how my thumb on my right hand is pointing negative j hat? Whoa, yeah, man. That torque will really get you out there, man. Does that make any sense?
Yeah. Think we're going.
Same old, same old. All right, so that's how you get the torque. That's what the axis means. So to be clear, that's the axis of rotation. Align right thumb with negative j hat, fingers curl in direction loop moves or in direction loop twists. So far, so good. And the rest is basically hard work, lots of it. So I have a bit of advice for you. A lot of you are probably the kind of students that like to try and do the problems without looking at the solutions ever, or maybe only once in a while when you get stuck. I put a lot of effort into this chapter's solutions because it's very, very tricky. There's a lot of right-hand rules. I would actually lean on the solutions a little bit more than you think in this chapter. And by that, I mean, start the problem, try to do it yourself. If you get stuck at all, read the solution immediately. And what should happen is after you do a couple of these problems, then maybe you won't need the solutions as much. But if you have to use them a lot to get through the homework, that's fine, because then you can take the practice tests without the solutions and make sure you actually know what you're doing. But I'm telling you, when you're reading the solution, you don't want to just be copying it down and not thinking about it. You have to think about everything in this chapter. It's like easy math, and yet it's very easy to get lost. There's so many directions. I mean, I beat myself up making these solutions in this chapter. So they, I think, are basically as good a chapter of solutions I've got. All right. Lots of big color figures like you're seeing on the board here. All right. Now, we got a little bit of time. What, 10 minutes? So I thought I might allude to another one here. And basically, let me go to, let's try problem 28.19, okay? Take a look at it. It's all about the directions. The math, I think, is pretty easy, right? It's just algebra. It's all about the directions. See how you can handle 28.19. See if that kicks your butt. All right, 28.19, page 146. I'm going to erase the board and get caught up. By the way, motors is one practical application of this problem. The other one is MRI. Yeah, NMR if you want to go that way.
Yeah, okay.
We'll get back to that at the end of the semester. We'll revisit that magnetic energy. To be honest, I don't put anything with magnetic energy on the next test, I don't think, but I do on the final. So I'll confirm that before I tell you that's for real. But I have to go back and look. Generally speaking, I tend to focus more on forces and torques from this chapter and not much on energy. But I think I have asked a question once in a while. I just don't know if it's only on the final or on the midterm. I'll check that. Wish there was more time. Triangular loop of wire, we got a coordinate system. 28.19, I think is what I said. Yes. This was an old test question. Pretty much all of these problems are on page, basically everything from 28.15 up to 28.20 are all old test questions. And basically every single time I put one on there, it would just, people get lost, people get lost, people get lost. So you gotta do all of them, right? You still might get lost. This is an easy thing to get lost. You got current flowing some which way. So we're told that this length is D. That means this length is the 3D. We got current. We are able to place a hinge on this loop so that it may rotate. There are two possibilities for the hinge. We can either put it on the x-axis or the y-axis. We can control both the external field and the hinge. This is starting to get somewhat realistic, right? The question becomes, where do you put the B field and where do you put the hinge or the axis of rotation, right? If you want to make this thing work, we have to think carefully about where we put the magnet and where we put the axis of rotation, right? The combination of those things matters. If you put it the wrong way, you could get a torque, but the hinge might prevent, right? What if we put the axis on the x-axis, right? What if our axle was right here and we get a torque this way? Well, having a J-hat torque and an x-axis, the axis is going to prevent the thing from twisting. Terrible motor design. Similarly, if we have an I-hat torque, but we use a J-hat axis of rotation, nothing's going to rotate. That's what this problem's about. So now the first question, which orientation of uniform magnetic field causes no magnetic torque about the x-axis? All right. Any ideas how we can approach this? Any equations that might guide our reasoning rather than guessing? Maybe we should write down the torque equation, right? Torque equation equals, what's the one that was useful last time? What's the easier one? Mu cross B external. Well, wait a minute. What do we know in this problem? We want this to have 0 in the I-hat, right? Nothing in the x-axis. It could have other stuff, right? But we want 0 in the I-hat. What about mu? What direction is mu? Negative k-hat. This is what we want. Now, obviously, I'm not writing the whole torque and I'm not writing the whole magnetic moment here. I'm just getting the direction of it, right? Right? So cross some kind of question mark here. So the idea is I want 0 in the I-hat. What can I not use? J-hat. Do you agree? Can't use B, Y, J-hat, or get torque in I-hat. Do you agree? If BY is non-zero, there'd be a J-hat in this equation. K-hat cross J-hat gives me an I-hat, and I want no torque in the x-axis. Isn't this a complicated question? This is what this entire chapter is like. Everything is hard to state. Everything is hard to read. But here, so basically, if BY equals 0, oops. anything in XZ plane is good. Agreed? That's what, so that's the answer. Is that one of the answers?
Yeah.
So it's basically telling us B needs to be in the XZ plane. What do you think? So far, so good? All right. Yeah. Moral of the story, when you see questions like this, you can write down an equation. Maybe it's a force question, maybe it's a torque question, but we could think about, mu and B and torques as directions only. And I do have a fun one for you to see here as well. Okay. Here's a weird one. All right. So here I have this big magnet, right? Now this is actually an aluminum ring, no power supply to it, right? If we all focus really hard, can you see this on Zoom? Yes, you can. Everyone focus on this aluminum ring. How am I? I've got a connected to a power supply right here. And what's happening is, this is dumb. The idea here is this is a transformer, and I'm actually turning this coil of wire called a solenoid into an electromagnet. But in the end, we haven't explained this. We'll get into this in about 2 weeks. But somehow, miraculously, this transfers energy into here and gets a current running. But right now, there's actually a current running through this ring, even though it's not connected to a battery. This is wireless power transformer. All right. So if you ever thought about how wireless charging works, we're going to get into that. But right now, do you agree there's an mg force down on this ring? And there's a magnetic force up?
Yeah.
Wouldn't it be interesting to try and understand how that works? Well, that's what problem 28.21 is all about. Take a look at it really quick. If you're curious about this one, that explains it. Oh my gosh. We'll learn more about this later, but this is kind of interesting too. Here, check this out. What do you feel? It's hot, right? That current, right? That's a very good, right? It's pretty hot. So what do you think is going to happen if I use this copper on here? Right? Copper is more dense, but it still works. It's a better conductor. We'll learn more about the issues associated with this. All right. Now, that's it for this class for today. And we don't have time to really do any more practice problems. But oh my gosh. Do the practice. That's all I can say. That's all I can warn you. All right. It's gnarly if you don't do it. Have a good one. We'll see you tomorrow in lab. No pre-lab. Okay.
Any problems you want us to do?
What's that?
Any problems you want us to do?
All the ones I said on the required list or whatever. I printed that out somewhere, but I think I lost it. Yeah, whatever I said was in the list. But don't be afraid about using the solution to get through it. Otherwise, it's going to kill you.
I meant for lab tomorrow.
No, nothing for that. It's just come in, learn to do arts and crafts. You're going to build one of these. Yeah.
Do you need a tip out, or can I ask a question about that?
You can ask a question really quick. Sure.
Okay, so why can't we use the area to find that? Is that basically with the XY plane?
Oh, you could have done that, right? Do you agree the full magnetic moment here is, hold on, let me, right? You're saying, couldn't I use this? So do you agree mu is equal to 1/2 d times 3d in the, what did we say? Negative k hat?
Yeah.
Yeah, absolutely. So we know what mu is. Right here, I was just getting the direction of it,
Oh.
right? So
okay.
if you want, take a look at this. This is going to be a little bit spicy here. I'm going to put unit vectors on here. Now, this is not always true, so I should be careful here. this is proportional to, you know what I mean?
Yeah.
So the idea is the direction of torque or torque hat should be proportional to the direction of mu crossed with the direction of B. Does that make sense?
Yeah.
So if I just look at the directions themselves, I'd say the direction of the torque relates to these directions. And that's what I was actually doing down here. Is that
Okay,
cool?
oh, you just missed that part then?
No, I just didn't say it. I was lazy.
Oh, okay.
Yeah, yeah. Is that good?
Yeah, that's totally good. Thank
Right,
you.
right on.
Appreciate it.
Yep.
See you tomorrow.
See ya. How about you Zoomers? Questions?
That was pretty crazy.
Yeah, right? Remember I told you, I was like, this is like the one time where reading before class can really,
Yeah,
it's too late now, right?
I know. Well, I did a little bit, but I need to go back. I just skimmed it, like you said, so I didn't get too much out of it.
That's good though. Skimming it probably helps a little, right?
Yeah,
Makes it a
this
subtle.
is yeah, this is gonna take me a while to figure out.
Yeah, use
But,
those
we'll get
solutions.
Yeah, all right.
Yeah,
Um,
Jose, we're done with this, this chapter. I may do like one more problem to start up as like a warm up on, Monday, just to kind of remind us, but generally speaking, we've done everything. We know about torque, we know about force, we know about magnetic moment, and that's what our goal was. Cool, Jose?
So we're moving on to 29 on Monday.
Yeah, yeah. And chapter 29 is like chapter 22 and chapter 23 all rolled into one. That's
Right.
why I give us an extra day for it.
Oh, Gauss's law. Oh, is that Ampere's law?
Yes, we're gonna do Ampere's law and the Biot-Savart law. Those are the, so Ampere's law is basically the equivalent, magnetic equivalent of Gauss's law.
Okay.
And then the Biot-Savart law or the BS law is the magnetic equivalent of like Coulomb's law and continuous distributions of charge.
Gotcha. All right.
So it's a
Cool.
lot of chapter 22 and 23 similar stuff.
Okay, sounds good. All right. Well,
We
I
actually
will.
have 3 class days for that one. So if I have to do
Okay.
a problem on Monday, it's okay, but yeah.
All right. Cool.
Yeah.
All right. Well, I will see you tomorrow in lab, and I'm just gonna go and practice a few of these and see if I can get it done.
Yeah, see if you can do a couple of them and then, yeah, we'll see you tomorrow. Should be fun
Yeah.
tomorrow.
All right. See you.
All right, later.